Hi, everyone. We're starting on Unit 5 today. Unit 5, extremely important regarding Chem 400. Extremely important. Along with the part of Unit 4 regarding balancing equations and grams to moles, moles to grams, that kind of stuff. That's also extremely important. You will see that not day 1, but probably day 2 in Chem 400. So those are really important. Okay. Excuse me. All right. So what we're going to do again, we're going to start Unit 5, which is called stoichiometry. Stoichiometry is kind of a fancy word. Basically, it is a term used to describe the processes by which we can forecast. If we start with this, what are we going to get? That's stoichiometry in non-chemistry terms. Okay, so let's jump over to this guy here. Okay, so I mentioned stoichiometry, and this is how to spell it. Frequently, they don't use stoichiometry. They'll use analytical reaction, quantitative reactions, but really, it's the proper term is stoichiometry. Okay, so this is a typical stoichiometry problem. When methane is burned in an oxygen atmosphere, carbon dioxide and water will always be produced. Now in Chem 400, I would have not given you the balanced equation. You'd have to figure out what the equation is. But in our class, I will give you the balanced equation. And it's unbalanced. Importantly, it's unbalanced, so you always have to balance it. Okay, so here we are. 12 grams of water is created. How many grams of methane are consumed? Okay, so we have methane is being burned, producing carbon dioxide and water. I'm telling you, we just made 12 grams of water. How many grams of methane does it take to produce 12 grams of water? So, when we do a stoichiometric problem, we have to do two main things. Balance a chemical equation and do a whole bunch of unit conversions. In this case, unit conversions are from grams of water to grams of methane. Okay, so remember we talked about the steps in a problem. And I said balance the equation. If there's no equation, we skip that part, and what's given, what's calculated, then we have the setup. It's the same thing for stoichiometry. Only in this case, we have a balanced equation we have to deal with. So step number 1 is balanced equation. Now remember the purpose of the balanced equation. Purpose of the balanced equation. In other words, you're asking yourself, Ferguson, why are we having to balance all these equations? Who gives a rip, right? Well, that comes into play when we start doing stoichiometric calculations. The stoichiometric ratio between the coefficients in the reactants and products are going to play a very important role in determining the answer to our problems. So a balanced equation gives us ratios between any of the reactants and products. And those are both molar ratios and molecular ratios. Molecular means I'm talking about the number of molecules. Molar means the number of moles between any of the constituents in reactants or products. Okay, so let's go back to our burning methane. Okay, so we got methane coming out of the wall on our fancy stove, our Viking $5,000 stove, and we burn that stove, and all of a sudden we produce 12 grams of water. We captured it, very fancy way we captured it. How many grams of methane did we consume to make 12 grams of water? Okay, so step number one is there a chemical reaction going on? If the answer is yes, then we have to write the chemical equation. So here we have methane, which is CH4, oxygen, excuse me, oxygen gas. Those are the reactants. And of course, we need a little spark. And when you get into 400, you'll talk about activation energy and all that good stuff, which is also known as spark. And that produces carbon dioxide gas and water gas, because it's going to be steam. And this is a gas, that's a gas. Okay, so is this balanced? Well, we have to check it. Okay, so we have CHO. Okay, we have one carbon, 4 hydrogens, 2 hydrogens, there's an issue there, 2 oxygens and 3 oxygens. Okay, so if we fix the hydrogens, since the carbons are fine, we put a 2 here, that jacks that up to a 4, and that changes our oxygens, because we have 2 oxygens here and 2 oxygens here, so that makes that 4 oxygens. Okay, so if we put a 2 here, that gives us 4 oxygens. So now it's balanced. Now, again, let's look at the balanced equation. What does that tell us? That tells us that there is 1 molecule of methane requires 2 molecules of oxygen gas. 2. And that will give us 1 carbon dioxide and 2 waters. If we have 1 mole of methane, it will be required to have 2 moles of oxygen gas. That will give us 1 mole of carbon dioxide and 2 moles of water. If we have 1.111 moles of methane, that'll give us 1.111 moles of carbon dioxide, because it's a 1-to-1 ratio. Okay, so bottom line is balance equation. Boom. If you don't balance the equation correctly, guess what? The whole problem is messed up. Okay, so it's important to balance the equation first. Step number 1. Step number 2 is, gee, this is like old world here. What's given? Okay, what's given? Well, it looks like 12 grams of water is given. What's being calculated? Well, grams of methane is being calculated. So now we do the setup. Now this setup is a little differently. This setup goes a little differently when we have a reaction involved. We have more steps. Okay, so step number 1 is we have to convert the given to moles. Okay, what's the given? The given is 12 grams of water, and I'm calculating grams of methane. I think we should have a green highlight. Okay. And then we do the setup. Convert given to moles. We use the mole ratio from the balanced equation. And then we convert moles of the calculated to grams or liters or whatever we're trying to calculate. Okay, so step number 1. Boom. Number 2. Okay, so that's given. It goes on the left. What are we trying to calculate? Grams of methane. That goes on the right. So, given to moles. It's not in moles, it's in grams. So we got to convert it to grams. Excuse me, convert it to moles. Now, I'm devoting 3 lectures to chapter 8. 3 lectures. Because there's a lot to this that needs lots and lots of iteration. Lots of iteration. And so keep this in mind as we're moving along. You're saying like, gosh, this is a pain, but we're going to do lots and lots of example problems. So that's 12 grams of water. And remember, step 1 is convert the given, whether it's grams, liters, number of particles, whatever, to moles. Okay, in this case, it's grams. We're going to be using the molar mass of water. Okay, so the molar mass of water is 2 hydrogens. And 1 oxygen. So that's 16 plus 2 water, 2 oxygen, 2 hydrogens at 101 apiece. So that's 1802. Okay, that's where I got the 1802 grams per mole. And notice the grams cancel, gives us moles. Now we have moles of given. Step 1 of the setup. Step 2 is the molar ratio from the balanced equation. From the balanced equation. The mole ratio from the unbalanced equation is superfluous. It does not work. You have to have a balanced equation first. Okay, so we're starting with water. We don't want water to end with, we want methane. So it's going to be a methane water ratio. You know, this is from the balanced equation. Okay, so methane is 1. Water is 2. Okay, so that's from the balanced equation. This is from the periodic table, the molar mass. Okay, so now we have, notice water cancels. What are what's left over here? Okay, well, we have moles of methane. Do we want moles of methane? No, we want grams of methane. So now this last step is we're converting moles of methane to grams of methane. Okay, and that's going to be grams over moles. And notice moles cancels. What are we left with? Grams of methane. And this is from P table again. So this is the molar mass of water. This is the molar mass of methane, CH4. Okay, so what is the molar mass of methane? Well, carbon is 1201. Hydrogen is 101. So that gives us, this ends up being 404, 1201, 1605. Grams per mole. Okay, so we have 3 sig figs, 4 sig figs, 4 sig figs. How many sig figs are in the middle, you guys? It's one of two answers, one or infinity.
Infinity?
Why? Correct. Why?
Okay, now you lost me. I had a chance, you know, 50% chance. So that
Right,
was
right. No. It's kind of a tricky answer. Because it's a perfect ratio. We didn't measure it. By definition, every 1 molecule of methane will react with 2 molecules of water. Not 1.1, not 1.00001, but exactly 1 to 2. So that means that has infinite significant figures. That means it doesn't come into play when we're calculating the significant figures. Okay? Does that make sense?
Yes, thank you.
Okay. All right. So our answer is going to be 3 sig figs. So what we're going to do is get out my handy dandy calculator. And we're multiplying 12 by 1 by 1605 divided by 1802. Hit the divide key again to enter. Okay, so we're looking at 534. Now, except for a very special case of stoichiometry, all the problems are the same. We have given, we have a balanced equation, we have what we're trying to calculate, and we grind it out in 3 parts. Now, in lecture 2.5 and 3, I'm going to talk about what happens if you have 2 givens. We have some special calculations to do. But right now, we're just looking at, we have a given. What are we trying to calculate? Here's the equation. Okay. All right. Are there any questions so far? Just by the way, feedback on your labs. I added a lab 4 video, and I added a lab 4 write-up and PowerPoint based upon a remote, lab experience. Okay, I added that a little while ago. Okay, so no questions about this so far, right? Okay, all right, so let's do another one. Okay, so we have the reaction of zinc metal in a copper nitrate solution. Metallic copper is formed and zinc metal dissolves. Now this would be a single replacement reaction. Okay, so we have a copper, just a real quick here. We have copper 2, copper 0. We have zinc 0, zinc plus 2. So zinc is losing electrons. Copper is gaining electrons. Okay, so all right, so we have our 4 steps of our stoichiometric process. Balance equation, what's given, what's calculated, and the setup. Okay. All right, so I've given you the unbalanced reaction. So is it balanced? Oh, let's see. 1 zinc, 1 copper, 2 NO3. That's actually balanced as written. Okay, so it's balanced. That means this is 1, 1, 1, 1, 1. Okay, so what's given? $599 grams of zinc metal. That's this guy here. Okay, and what are we trying to calculate? Trying to calculate copper metal. So we're going from this zinc to copper. Given, it doesn't matter about that other stuff. Doesn't matter. All we're looking for is what's given. And you ignore everything else. Okay, the zinc's what's given. What are we trying to calculate? Ignore everything else. Trying to calculate copper metal. Doesn't matter about the zinc nitrate and the copper nitrate and blah, 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 blah. Don't have to worry about any of that. Okay. All right, so that's step number 1, balance equation. Okay. Number 2, what's given? Now I'd like you to put up here the zinc, because we're going to actually cancel that. Okay. Now, step number 1 in the setup, that's what we're on right now, is converting what's given. In this case, it's grams, but again, it could be, we could have, excuse me, atoms of zinc. We could have liters of zinc gas at some ungodly high temperature. You know, 6,000 or 7,000 degrees centigrade. Zinc metal would probably be gaseous. Whatever. We need to convert that to moles. Okay, if it's in grams, we just use the molar mass for zinc. Okay, so here's zinc. And zinc is 6539. Notice grams have got to be in the bottom because it needs to cancel. Okay, so this is molar mass of given, whatever it is. Get that from the periodic table. Okay, step number 2 is from the balanced equation. Now I want you to be careful here, because the balanced equation is 1, 1, 1, 1, 1. one would think we wouldn't have to include this step, but we do. The reason we have to include it is because our unit cancellation won't work out unless we include it. Because the ratio is copper to zinc. See, now our zinc cancels. And what's our ratio of copper to zinc? 1 to 1. This is from the balance equation. So what do we have here? We have moles of copper. What do we want? We want grams of copper. Okay, that means that we're going from moles to grams. That's a molar mass of copper. And copper is right next to zinc. And it's 63.55. Excuse me. Excuse me again. Okay, so notice our moles cancel, leaves us with grams of copper. What are we trying to calculate? Grams of copper. So our units work out. And again, 90% credit. And this is molar mass in the periodic table. So we have 3 sig figs, 4 sig figs, infinite sig figs, and we have 4 sig figs. So our answer is going to be 3 sig figs. So we're going to grind that baby out. So it's going to be 5.99 times 1 times 1 times 1 times 63.55. And divided by 63.39, or excuse me, 65.39. Divided by 1, divided by 1. Okay, so our answer is 5.82. Grams of copper. Okay, now I want you to look. Are there any questions about what I've done? Okay, was everyone able to follow what I've done? I'm not saying do it on your own. I'm just saying, were you able to follow what I've done?
Yes.
Okay, good. And you are representing the whole class. Okay, all right, look at these two problems. Okay, look at this guy here. And then look at this one. Gee, don't those look similar? Really similar. Really similar. Now, I posted some extra by the way, this is me in my tie-dye lab coat. This is an additional worksheet I posted. I don't think there's enough example problems in the official problem set for chapter 8. Now, so it's taking a second to load because it's a PDF. More than a second. Okay, so I've given you, oh my gosh. By the way, this problem I balanced for you because it's a pain to balance. I didn't want you to spend 10 minutes balancing that equation. Okay, so I've given you, I don't know, 15 problems or so. I want you to look at the answers. Okay, look at those answers. The setups here. Look at how much they look like what we've just done. Every single one. Every single one is the same setup. 3 steps. What's given, convert to moles. Mole ratio from the balanced equation, then convert to what you're trying to calculate. Every single one. Every single one. And this is an extra step because we're going from kilograms to grams because the molar mass from the periodic table is in grams per mole. So we need to convert to grams here. But it's basically given mole ratio from the balanced equation, convert from moles to what's being calculated. Every one of these. Okay. All right, so that's extra. Okay, so now I want to back up a second and look at this from a really kind of a plebeian perspective. If I had, let's think about a bicycle. So we have 2 wheels, 1 frame, 1 handlebar. And then we have one total bike. So it takes 2 wheels, a frame, and a handle for a total bike. So that is kind of our equation. So we're going, let's call these W's, F's, H's, and V's. So we have 2 wheels plus 1 frame plus 1 handle gives us 1 bike. So I could ask you a similar question. If you have 18 wheels, how many bikes can you make? All of you can do this in your head. You go, oh, 9. Oh, why? Because it takes 2 wheels per bike. And 2 and 18 goes 9, right? That's the same as this. It's the same as this. Okay, I've related wheels, bikes, wheels, frames, handlebars to number of bikes. It's that relationship. Okay, so we can do this. We have 18 wheels. And it takes once the wheels cancel, what do we have left? Number of bikes. So 18 divided by 2 is 9 bikes. Okay, so we have given and calculate it. So the process is exactly the same. You're doing this in your head, but the process by which you're going through logically is this. Okay, so let's do one more problem. And then between now and Wednesday, I want you to do as many of these problems as possible. It's really important to do as many as possible. And the reason for that is we are going to get into a slight nuance the second part of Wednesday. And then full blown next week. Okay, so let's do let's see here. Oh, I already have one already done here. I did a copy and paste from a previous lecture, and I thought, let's see here. Let me erase this one. Okay, how many grams of ethane are in 1.21 molecules of ethane? Okay, so this, I want to go through this really quickly as a front end to the stoichiometry problem. Now this is just a conversion. This is no reaction. This is no reaction. I'm not burning ethane. I'm just saying, if I got so many grams of ethane, how many molecules do I have? Okay, so just as a review from unit 4. Okay, so what are we starting with? We're starting with ethane. And I want to know grams of ethane. Okay, so okay, and how many, now to get grams, we can't go from molecules to grams, we need to go through moles. So we need to convert the molecules first to moles. And that's going to be okay, Avogadro's number. Now we have moles. Now we can go to grams. And that grams to moles is from the periodic table. So carbon is 1201. Hydrogen is 101. And 2 of those and 6 of those. 2 of those is 2402. 6 of those is 606. So that's 8. So that's 30.08 grams per mole. Okay, so let me quickly do that. And because I'm going to now branch off from here. I'm going to do a full-blown stoichiometry problem using molecules instead of grams. Okay, so we're looking at, this is 3 sig figs, 4 sig figs. So answer is going to be 3 sig figs. That's going to be, what is it, 605. Okay, so we're looking at 605 grams of ethane, C2H6. If we start with 1.21 times 10 to the 14th molecules. Okay, so what if we turn that into a stoichiometry problem? Okay, so I have a whole bunch of problems here I pre-set up. Let me quickly dispose of that. Okay, so okay, so basically it's the same thing as burning methane, only ethane is a little bigger molecule by 1 carbon. Same reaction though, okay? So how many molecules of water are produced if 3.45 grams of ethane is burned? Okay. Now, I gave you that problem up here as a review, because we're going to be converting from molecules to moles and all that stuff. Okay. So step number 1 is what's the reaction? I already told you I was going to give you the reaction, unbalanced reaction. So that's C2H6 plus O2. Let me do my little and that produces CO2 plus water Okay, so is this balanced? Well, just looking at it, no, because we have 2 carbons here, 1 carbon there, so we need to balance this guy. So we have, okay, so we have 2 and 1, 6 and 2, 2 and 3. Okay, so I'm going to put a 2 here to bring our carbons up. That changes our oxygens though. So that's 4 and 1 is 5. And we have 6 oxygens. So let's put 3 here to kick our oxygens up to 6. That changes our oxygens again. Okay. So now we have 4 and 3 is 7. So what do we multiply 2 by to get 7? Well, 3.5. Let's make some more room here. And somewhere over here. And this could be like that as well. Okay, so it's balanced now. As 3.5 times 2 is 7. Okay, so we have to get rid of the fractions. So that means we're going to multiply everything by 2. Okay, so that makes that 2. 3.5 times 2 is 7. 2 by 2 is 4. 3 by 2 is 6. So we have 4 carbons, 12 hydrogens, 14 oxygens, 4 carbons, 12 hydrogens, and 8 and 6 is 14 oxygens. So it's balanced. Okay. All right. So step number 1 is balance the equation. All right. What we're going to do now is what's given. That's what's given. Okay. What are we trying to calculate? Molecules of water. So what's germane to this whole thing is water and methane. We don't care about the oxygen, the O2, or the CO2. We don't care about that. So what are we starting with? C2H6, 3.45 grams. Okay, step number 1 is balance the equation. Check. Step number 2 is convert the given in grams to moles. Okay. We already did. Okay, so C2H6 is 30.08. Okay, and that's from the periodic table. Now we have moles of ethane. Next step is the mole ratio, or the coefficient ratio from the balanced equation. Ethane to water is 2 to 6. So we want ethane is on the bottom to cancel, and then water is on the top. Now we have moles of water. We want to know molecules of water. We want to go from moles to the number of molecules. That's 602. Per mole. Moles cancel. What does this give us? Gives us molecules of water. What are we trying to calculate? Molecules of water. Okay, so let's see how this thing grinds out here. So we're looking at 3 sig figs, 4 sig figs, infinite sig figs, 3 sig figs. The answer is going to be 3 sig figs. Okay, so we're going to go 345 times 6 times 602 EE23 divided by 3008 divided by 2 divided by 1 equals, okay? So it's going to be 207. .07 times 10 to the 23rd molecules of water, 366. So it doesn't what you start with, doesn't matter what you end with, it's the intermediate mole conversion along with the balanced equation. That's the underlying theme on doing every single one of these problems. Is what are you starting with? Convert to moles. Mole ratio from the balanced equation, and then go from moles to whatever you're trying to calculate. 3 steps. Okay, so what I want you to do between now and Wednesday is work some of these problems. I would suggest starting with the ones that I gave you separately. That'll give you lots of practice. Okay, so again, on Wednesday, I'm going to be taking this to another level. So on Wednesday, I'm going to assume you've done lots of problems, so you're comfortable with this process. The trick on Wednesday is going to be, I'm going to give you 2 givens instead of 1 given. So you have to deal with each given separately and figure out some stuff. It's called limiting reactant. And again, you will be quizzed on this week 1 of Chem 400. You'll be given a stoichiometric quiz. It probably won't be a limiting reactant like for Wednesday. It'll probably be a problem similar to the ones we did earlier today. So this is a big deal, this stuff, you guys. Big deal. When I used to teach Chem 400 on a quarter basis, 80% of my class was on stoichiometry. 80%. Now, being a semester, there's some other stuff involved because it's a longer than a quarter, but still, there's a big chunk of first part of Chem 400 is stoichiometry. Okay. All right. So are there any last minute questions? Are there any questions?
Nothing from me. Yeah.
Okay. Was it reasonable?
Yes. And definitely with some practice, it's going to click more.
Yeah, but you were able to follow me though, right?
Yes, definitely.
Okay, cool.
Each step made sense.
Okay, all right. Because if you can follow me, it's just a matter of doing a zillion of them. Yeah, that's how I learn. And so I'm assuming my students learn the same way. Do a zillion of them. And you will see all of a sudden things fall into a pattern. And that's why I went to that point of showing you all those problems, the answers, how they all fall into the same deal. 3 steps. Balanced equation setup is in 3 parts. Boom. Every single time. Okay. All right, so I'm going to sign off, but you guys go ahead and really do those. I highly recommend it. Wednesday's lecture will make so much more sense if you practice those. Because when I'm, instead of 15 grams of methane, I give you 15 grams of methane and 15 grams of oxygen. How much water did we make? I know, it's okay. All right, everyone, take care. And have you all gotten used to the new time thing?
Yeah, it's actually really nice because I'm an early to bed person. So it's dark for like 3 hours now before I go to bed instead of like 5 minutes. So
it's so different. Like, when is the solstice over the summer? It's like, isn't it June 20th or something like that?
21st, somewhere around there usually. Yeah.
Yeah, it's just
I
crazy.
It's weird. I'm actually enjoying it kind of this year, even though I think I have a little bit of the seasonal depression. Like I have to kind of make myself go out and do things in the winter. It's kind of harder to get started. Um, but I don't know. I'm kind of enjoying it this year. I was sick of the heat.
Well, up in Washington, because it's so much higher latitude, it would get dark by 4 o'clock in
That's a
December.
bit much for me. Yeah, I want to
Yeah.
drive home I don't want to drive home in the dark from work.
Yeah, and in the summer, it wouldn't get 10:30 at night. It's still twilight.
I would have trouble sleeping properly in the summer then. Yeah.
Yeah, I mean, it's because it's so far north. A lot of people don't realize how north it is, but it is amazing how the time changes so much. And they're getting blasted with weather.
Yeah, I've seen some of the news about that, and grateful I live in such a moderate climate.
They're getting feet of water. Yeah, feet, and throwing some wind. 50,000 people are out of power. Oh my God, it's. I'm down here, over the weekend we went wine tasting, in the sun.
Very nice.
Music in the background, a little jazz. They're up there pouring and it's 45 degrees.
Yeah.
Anyway, sorry, all my friends up there. No.
Yeah.
All right. Anyway, all right, you guys take care. But I highly recommend trying to do those practice problems. Just do as many as you can. Fit in as many as you can. It really will make Wednesday lecture much clearer.
Got it.
So, all right, everyone, take care.
Have a good night.
Yeah, you too.